Stanford University.
All right, so what is particle physics about? Particle physics is about particles. It's about the question, and this is a very ancient question, at least, I suspect, about 2,500 years old. Is nature discrete? Discrete meaning to say not that it's polite, but that matter and substances and energy, they didn't think about energy, but they thought about matter. That matter comes in discrete units, in indivisible units, which of course the Greeks called atom. I'm told that the word atom means indivisible, despite the fact that, of course, we break up atoms all the time. Nevertheless, that was the origin of the word, indivisible, that all things in the universe are made up out of something discrete. Let's call them particles. Particles is a good name for something discrete, something indivisible. That idea is, as I said, extremely ancient. The opposite idea is also ancient. Again, I don't know precisely when it was first formulated. I happen to remember a little more about the history of the atomic idea. That was, it doesn't matter who it is. Incidentally, do not trust my history. Not because I don't know the history, but I sometimes tell the history in which I organize things logically rather than temporally. So don't trust the time sequence that I tell you. It often represents what I wish the time sequence was rather than what it actually was. But it's good for to present the logic of what happened, to present it in a logically compelling way rather than a strict historical way. In any case, there were these characters who were the atomists, and the opposite of them, the people who thought that matter, material, and so forth was continuously distributed. Continuously distributed means simply not made up out of discrete elements, but I don't know what the right word is. Uniform, continuous is the right word. A schmear, as my grandmother would have said. A schmear. Smeared out over space in some uniform, continuous kind of way. And we might call that the field theory of matter. Fields, what are fields? Fields are functions in space. For example, they could be the density of material in a given region of space. They could be the electric and magnetic fields. Those are good examples. Electric and magnetic fields that determine how charged particles move. But the fields themselves, the electric and magnetic fields, are things that we conceive of as being uniformly distributed in space, not in the form of particles. And so perhaps matter, liquids, solids, and so forth, are also in some sense continuous, just like the electromagnetic field. That was the opposite idea. The particle idea, the discrete idea, had words like molecules, atoms, and so forth, collisions, and particles. The continuum idea, continuum is the right word, the continuum idea had words like fields attached to it, continuous fields of properties of various kinds. Which turned out to be right? In some sense, neither and both. In some sense, neither and both turned out to be right. The subtleties of quantum mechanics got in the way of either of them being completely right, but it also got in the way of either of them being completely wrong. Quantum mechanics is a subtle and difficult subject, as are many of the preliminaries to particle physics. I think I have taught all of them by now several times, and they do exist on the internet. The internet lectures that I've given, they're out there, and I advise you, as I said, I will try to keep it self-contained, but I am going to assume to some extent the knowledge that I have taught previously in these classes. It can be picked up off the internet very easily. I don't know how to do it. I couldn't do it for the life of me. I can never access my own lectures. but everybody else can do it. And well, the real reason is I don't like looking at myself, so I never do open my own lectures. But they're out there, and they're fairly complete. There are at least 2 courses out there on quantum mechanics. I think 1 on classical mechanics, at least 1 on special theory of relativity and electromagnetism. So since I put that effort in, I'm now going to try to draw on it, not today, but in the future, and use many of the things that I have lectured about. Okay, as I said, the particle physics question is whether nature is discrete or not. Let's just do a little bit of history, which I will probably get wrong, but that's at least chronologically. To my knowledge, the first real evidence, again, it's to my knowledge, the first real evidence that matter was discrete came, of course, from chemistry. It didn't come from physics, it came from chemistry. The division between chemistry and physics is a highly artificial one. Chemistry is simply just basically the physics of atoms and molecules. But it came from the chemist, or John Dalton? John, I think. John Dalton, who realized that the masses of chemicals, the mass of a given number of molecules, Now, how he knew that he was had to deal with a given number of molecules when he might be talking on the one hand of hydrogen, on the other hand of carbon dioxide or something, how he knew it was a given number of molecules is itself a story. Avogadro's name comes into it and so forth. The word mole, not the creature that lives under the ground, but the mole is Avogadro's number of molecules. How they knew how many molecules, they didn't know how many molecules, but how they knew how to compare different substances and say both of them had the same number of molecules, that itself is an interesting story, but it's not the story I want to tell. The story I want to tell had to do with the mass of a mole of material, a mass of a given number, Avogadro's number of molecules, that it came in discrete multiples of the mass of a mole of hydrogen. Now, not exactly, but close enough to a pretty good precision. The mass of a mole of gobbledygook is a integer multiple, not three halves, not pi, not some other silly number, but some integer times the mass of the same number of molecules of hydrogen. It sort of suggested to Dalton that there were building blocks, that carbon, what is it, carbon 8? Carbon 12. Carbon 12 had 12 units of whatever hydrogen 1 had. Hydrogen was 1 unit of stuff, whatever that stuff was, carbon 12, and whatever the other numbers were. So it seemed like things were being built up out of basic units, which basically had the same mass as a hydrogen atom, almost as though everything was made up out of units of hydrogen. Dalton, I think, proposed something like that there were basic units, and those basic units had the mass roughly of a hydrogen atom. So that was the first bit of evidence, and of course this was essentially right. Today we understand, let me just tell you why that's true from today's perspective, not to make a mystery out of it. Everything is made out of atoms, and atoms are made out of protons, neutrons, and electrons. Electrons are very, very light compared to protons and neutrons, and in counting up the mass of an atom, the electrons are not very significant. An electron has about a mass of 1/2000th. 1/2000th of the mass of a proton or a neutron. So electrons don't come into the equation. They do come into the equation, but only a very, very small term. Forget about them. Protons and neutrons constitute most of the mass, almost all of the mass of ordinary material. On the other hand, protons and neutrons, surprisingly, there is a good reason for it, but at the time there was certainly no known reason. In fact, protons and neutrons weren't known. But protons and neutrons have about the same mass as each other. As I said, about 2,000 times the mass of an electron. And so the mass of a molecule is basically the mass of protons plus neutrons. They have about the same mass, and therefore the mass of a molecule is an integer multiple of the mass of a proton and neutron. On the other hand, the nucleus of hydrogen is just one proton, and so it did turn out that Dalton was right. All materials have a mass which is approximately, there's an approximation in there. Protons and neutrons don't have quite the same mass, slightly different, less than 1%, incidentally, 0.1% or even less, whereas electrons are so light that they don't come into it very much. And so Dalton was right. And it was the first, to my knowledge, the first real evidence that matter came in discrete units. Okay. Now, molecules weren't atoms, of course. It took a little while longer to find out that molecules were made up out of atoms, and the atoms weren't just protons and neutrons or hydrogen, that atoms themselves, the things we now call atoms, that there were about 100 of them, 100 different kinds. This was, of course, the great triumph of chemistry of the 19th century and early 20th century to identify all of the elements that go into the periodic table up there. Incidentally, the periodic table is not very periodic. If you really look at it, it's a bit of a fake, the periodic table. It's not very periodic. But nevertheless, identifying all those separate atoms up there, the elements are in some things which are composed of all the same kind, you know that story. They're composed of atoms, and identifying the atoms, and at the end of the identification of atoms, roughly about 100 of them, less than 100 occurring in nature, 92 of them to be precise. Well, more than that if you include isotopes, but of order 100 different kinds of atoms, and everything made up out of atoms. So atoms, at the end of the 19th century, the things we call atoms or elements were the building blocks, the elementary particles of nature. Now, of course, it took another 5 years after the turn of the century for Einstein to do something that really nailed the molecular theory of matter. It wasn't until 1905 that Einstein explained in detail how you could prove that matter was really made out of particles. But long before that, chemists, physicists understood, for the most part, that everything was made out of these 92 elements. So they were the elementary particles. Now, sort of all hell broke loose in the beginning of the 20th century, very end of the 19th century, when some discoveries were made. The electron was discovered about 3 years, I think, before the turn of the century. I don't know exactly when it was. The electron was discovered, and a number of other things were discovered, but in particular, radioactivity was discovered. Radioactivity was the first real signal of the thing which was later to become nuclear physics, and particle physics, and had all the things that needed to be explained sort of there in a sort of tiny little version. So let me just remind you about radioactivity, just for fun. Who was it who discovered radioactivity? I don't even remember. I don't think it was Marie Curie who discovered radioactivity. I don't think so. Was it Becquerel? I think it was Becquerel. Yeah. I don't think it was Marie Curie. What she did was, lots and lots of experiments to pin it down with but it was Becquerel. And he had a chunk of lead. Don't ask me why he did this. I do not know. He had a chunk of lead and a little hole in the chunk of lead like that, and some material down here. Radioactive. I guess the first thing that happened was he had some radioactive material, presumably radium or something like it, in his laboratory, and he had a photographic plate, and accidentally the photographic plate happened to be near the material, not here, over here, material, photographic plate, and the photographic plate got ruined. Got ruined by the presence of the radioactive material. The radioactive material just ruined, was like light shining on it and ruined the photographic plate. Anybody else, or not anybody else, probably me, would have just thrown away the plate and said, this is ruined, let's find another plate and start the experiment over again. But Becquerel realized he had discovered something. He had discovered that radioactive materials do something to the photographic plate as if they had been illuminated by some radiation. So he decided to study that radiation a little bit better, and he put the source of it deep in a block of lead. How he knew to use lead, I do not know, but lead was a good substance because it's very dense. And he put it into a hole, drilled into the lead, and then put his photographic plate out here, and wanted to see whether it would illuminate a single spot over here. Everything was collimated by this hole. He wanted to see whether it would create a sharp little spot as if something were coming up out of this hole. And indeed it did. So he got the idea that a beam of some sort was being ejected, or something was being ejected by this radioactive material and being collimated along a beam. That was the first particle beam. That was the first beam of particles. All right, what was it? He had no idea what it was. But then I guess a second fortuitous accident, I think it was an accident, again, I'm making up the history as I go along, but it's close to the truth. He happened to have a magnet in the laboratory. And for some reason, the magnet was in a position here where a magnetic field was created near where these particles were being ejected. And what happened when he put the magnetic field, when he put the magnet near this, is the beam split into three separate beams. Three separate beams. One went straight ahead, just as if the magnetic field was not there. One of them got deviated to the left, and one of them got deviated to the right. Left, right, left, whatever. One deviated more than the other, in fact. They were not symmetric. And Becquerel, or somebody, whoever was around, knew enough to realize that beams of particles, trajectories of particles, get bent by magnetic forces. If you have a magnet and you have a charged particle, the charged particle goes through the magnetic field and either bends to the right or to the left, depending on the sign of the magnetic field and the charge of the particle. So if the particle was a positively charged particle, it would bend one way in the magnetic field. If it was a negatively charged particle, it would bend the other way in the magnetic field. And what Becquerel had found is that there were three kinds of radiation. One behaving as if it was composed of electrically neutral particles. Which one was electrically neutral? The one that wasn't deviated at all. Of course, he didn't know they were particles. All he knew is that some collimated effect happened that illuminated the detector, the screen, the photographic plate. One of them got deviated to the right as if it were a negatively charged particle. He called that component of the radiation, he called that component beta. The component that went straight ahead, he called gamma. And the component that deviated in the other direction as if it were positively charged, he called alpha. These became the three distinct kinds of radioactive effects, the three distinct kinds of radioactivity: beta radioactivity, gamma, and alpha. Just again, I'm not interested in making suspense here. Let me just tell you what they were. You probably know what they were. Many of you know what they were. Beta was electrons, negatively charged particles, which were just the electrons that had already been previously discovered from cathode ray tubes and that kind of thing. And these were electrons coming out. The alpha particles, we now understand, and at that time there was no precedent for it, that they are helium nuclei, 2 protons and 2 neutrons stuck together. Atomic number 4. Dalton would have, had he had access to helium, which he didn't, he would have said helium was number 4 on his integer collection of materials. And gamma are photons, okay? Electrically neutral, no electricity at all. And these 3 kinds of, now, I think he did, again, I don't remember the history, but he might have had a sufficiently dilute source that these particles arrived one at a time at their destination. And in that case, he would not have seen a bright spot over here. He would have seen blip, 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 illumination occurring or spots occurring, discrete little spots occurring for the electrons. And he might have said, oh, those are particles. Particles arriving one at a time, illuminating the screen discretely. He would have done exactly the same thing for the alpha particles. He would have found that the alpha particles arrived one at a time. In other words, he could have used, he might have used, he probably did, use the screen here as a counter, analogous to a Geiger counter or something. Whether he did or not, I don't know, but it's something you can imagine, that he detected the particles coming one at a time. That would certainly be feasible with a Geiger counter. And so evidence that whatever this radiation is, it's coming in discrete little bundles that we could call particles. What about gamma? Same thing for gamma. Gamma is coming one at a time, but at that time, Becquerel had no idea, neither did anybody else, what gamma was. It was uncharged, that was all that was known, and it illuminated the screen just as the others did. Okay, that was, as I said, in some sense, the first particle physics experiment. We'll come to some later particle physics experiments soon enough. Let's next talk about electromagnetic radiation, ordinary electromagnetic radiation. Oh, well, I said I wasn't going to make suspense. Gamma is photons. Gamma is light. Gamma, well, it's very high energy light, but gamma is in some way connected to ordinary light. So let's come to light. Gamma was the big mystery because there were no neutral particles known at that time that could account for the gamma radiation. And so gamma was a mystery. And that mystery persisted until fairly late in the very early 20th century. Let's put it that way. Fairly late in the very early 20th century. It was, of course, Planck and Einstein, really Einstein, who were the first to understand that light comes in quanta, that light comes in photons. But let's go back. Light was sort of the strong case for something which was not made of particles. Light was something which was clearly made of fields. It was made of the electromagnetic field. Okay, the electromagnetic field, electric fields and magnetic fields, forming waves. When you shake a charge, waves get given off. The wave fields are continuous wave fields, at least according to classical electrodynamics. And they give off waves that propagate through space completely continuously. And Newton, of course, had thought that light was particles. But Newton, by that time, had been completely relegated to the dustbin, at least as far as theory of light went. There were many experiments, some of them done by Newton himself, that strongly said light is waves, not particles. So let's just talk about light a little bit. Electromagnetic radiation. If you take electromagnetic radiation, it comes in waves. So if there's a source of electromagnetic radiation here, an antenna, some form of antenna emitting, could be radio waves, it could be microwaves, it could be infrared, it could be light, it could be ultraviolet. An atom is a perfectly good antenna, incidentally. It doesn't have to be a big macroscopic tower. An atom with a charge going around in a circle is an antenna. Antennas emit waves, and those electromagnetic waves, when they also fall on a photographic plate or other device which is sensitive to light or sensitive to radiation, will illuminate that, and turn it white or black, turn it black, I guess. And that's in the character of light. Now, how do we know that these things are waves? How can we tell that they're also not bullets shot out of the source here? So one thing you might do is do something very similar to what was done over here. Put an obstruction, a little hole, and see whether the light is collimated exactly as if it were bullets being shot out of the gun here. If it was bullets, you would illuminate a little spot over here. And of course, what happens is that you don't illuminate such a small spot. You illuminate something which is fuzzier than that. You illuminate a fuzzy region. But that in itself did not prove that light was waves. Not at all. You could say, well, just maybe when these particles go through this opening here, maybe they have little forces exerted on them by the edges of the hole here or whatever, which deflect them. Some of them get deflected, and so maybe you get a more smeary picture, a more smeary image than you might have hoped for. So it was not just that the beams got deflected, the light beams got deflected. That in itself was not enough to argue for a particle structure to light, or sorry, a wave structure to light, I'm sorry. But you do something else, which is much more sensitive to the wave character of light. Here's the screen over here again. You open up two little holes next to each other. If light was simply particles, what you would expect to find here is basically two smears of the same kind, just superimposed on top of each other, maybe a little extra dense in the center where they overlap, but just two smears, one the image of this hole, one the image of that hole, with nothing unusual. Okay. This, of course, is not what happens. What happens is each hole emits waves. You could do the same trick with water waves. In fact, it's not hard to do the same trick with water waves. And the water waves interfere. If this is the high point of a wave coming out of here, and this is the low point of a wave, places where the high points combine from the two holes reinforce each other. Places where a high point from one hole meets a low point from the other hole cancel each other. And so the effect is to see, when it hits the screen here, to see bands. Bands of positive reinforcement where the high points add, missing places with no light where the high points meet low points. Okay? That's an interference pattern. An interference pattern is a real signal of wave-like motion, of wave behavior. Waves, you can do this, as I said, with water. You just put your finger into water and wiggle two fingers, and the two waves from the two will spread out. Some places they'll reinforce, some places they'll cancel. And so rather peculiarly, but nothing terribly unusual, places which would have been illuminated by either of the two holes by themselves, there's destructive interference, they get canceled, and places you get constructive interference and they add, and you get extra intensity. That is the kind of thing, this interference property was the kind of thing that really nailed the wave theory of light. Okay, so light was a wave. In fact, this did not occur after Newton. It really occurred before Newton. Huygens was a 17th century? Huygens must have been 17th century, but previous to Newton.
1808.
Who? What?
Thomas Young,
Yeah.
the physicist,
Yeah.
that demonstrated the interference of light.
Yeah, but Huygens already had the basic ideas of wave propagation, and that's from the 1600s sometime. So this debate went back, and Newton had done many experiments himself, which should have been interpreted as interference, wave interference, but he didn't. In any case, after these experiments, Young's experiment, others, it was definitely confirmed that light is made of waves. Okay, what kind of waves? Well, that took Maxwell. Maxwell realized that they were waves of electric and magnetic field. You know what an electric and magnetic field is? An electric field, well, look it up if you don't know. Electric and magnetic fields. And light is a wavy motion of electric and magnetic fields. First of all, light is a wave. And here's a wave moving down the axis. What is that wave a wave in? Well, it's a wave of electric field. Here the electric field is pointing down. Here the electric field is pointing up. Here the electric field is pointing down. Let's just draw a line through there. Alternating electric field, up, down, up, down. And the whole thing moves off with the speed of light. The whole thing moves off with the speed of light. Electric field, incidentally, there's also a magnetic field attached to the thing. It's a complicated object. It has magnetic field also. The magnetic field is perpendicular to the electric field, and so it sticks out this way. And that's what a light wave would look like if you could sample its electric and magnetic field as it went past you. Of course, as it passes you, it will constantly alternate very rapidly if it's an ordinary light wave, much too rapidly for you to be able to see. But if it were an extremely long radio wave, very, very long radio wave, you might be able to see the field oscillating in front of you. And this is, as I said, what it would look like. It's a wave. Being a wave, it will exhibit interference patterns. And Maxwell had absolutely nailed the wave and the electromagnetic theory of light. So let's talk about waves a little bit before we talk about particles. Let's talk a little more about waves and the properties of waves. The first property of a wave that I want to come to is the wavelength. Wavelength is simply the distance along the wave before you return one full cycle to the next wave. All right, so you start here and you go and you come back to the same exact kind of thing as over here. That's one cycle or one full wavelength. And the wavelength, for symbol for wavelength, is lambda, Greek lambda. Okay, lambda for length. That's the wavelength, and it's measured in units of distance. It's measured in meters, or it's measured in centimeters, whatever your choice of units are. Okay, so lambda equals wavelength. Wavelength, let's just call it wavelength. Another property is if you were to stand still and just watch the wave go past you, the head would go up and down and up and down and up and down. It would have some frequency. How many cycles per second? This is not the length of the wave in space. It's kind of the number of cycles per second, or perhaps even something simpler, the time that it takes to go through one cycle as it passes you. That could be called the period of the wave. Period. It's a time. It's measured in seconds. So, and a light wave has a very, very short period. Up and down, extremely fast, 10 to the minus 15 seconds or something, whatever. The longer the wavelength, the slower the period. The shorter the wavelength, the faster, the The shorter the wavelength, the shorter the period. Okay, what's the connection between wavelength and period? Okay. Yeah, right. So think about the wave moving past you, one wavelength. How far does it move? It's moved distance lambda. How long has it taken? It's taken the period. The distance that it moves divided by the time that it takes to move that distance is the velocity of the wave. For light, that would be the speed of light. If it's not a light wave, it might be moving with different speed. If it's a water wave, it would be much smaller speed. If it's a sound wave, it's a smaller speed. But for a light wave, the wavelength divided by the period is always equal to the speed of light. Whatever the wavelength is, the period is given in terms of the wavelength, or the wavelength is given in terms of the period. So that's a fundamental relation. It's usually expressed a different way. The inverse of the period, 1 over the period, is called the frequency. It's the number of waves, it's the number of oscillations per second. The number of oscillations per unit time is called the frequency, and that's equal to 1 over the period. Faster the period, the shorter the frequency, and so you can also write this as the wavelength times the frequency is equal to the speed of light. So if I give you the wavelength, you can tell me the frequency. If I give you the frequency, you can tell me the wavelength by solving this equation. And that's the fundamental connection between wavelength and frequency. Now, since one of the things that I really do want to teach you a little bit is the terminology that physicists use for things, and they tend not to use the terminology of cycles per second for frequency. They use something else. It's radians per second. What does that mean? Imagine a thing going around in a circle. It's going around in a circle with a frequency f. That means f times around the circle per second. Physicists and mathematicians tend to use not the number of times you go around in a second, but the number of radians. Radian is about 57 degrees. It's an angle about that big. How many radians per second? And the relationship between the frequency in terms of cycles per second and the frequency in terms of radians per second is very simple. In terms of radians per second, we call it omega. And they're closely connected to each other. Omega is just 2 pi times the frequency. Why 2 pi? Because there are 2 pi radians in a circle. So frequency can be measured in either way. Physicists tend to use omega, except when they're writing elementary physics books for undergraduate pre-med majors, in which case they use f. Okay? We're all physicists, we're all grown up, we're all, so we can use omega like the world of physics does. Omega is the frequency of the light measured not in cycles per second, but in radians per second. You say, where is the angle for a light wave going away? Don't worry about where the angle is, just divide frequency, or just multiply frequency by 2 pi, and that defines omega. All right, they're proportional to each other. All right, so we can also write this then as, let's write it this way. Frequency, I'm going to write it, frequency is equal to c divided by lambda. And now I'm going to substitute for frequency omega divided by 2 pi. And what do we get? We get omega is equal to 2 pi c over lambda. Fundamental equation of wave motion, that the frequency measured in radians and the wavelength are related by 2 pi times the speed of light. This, of course, is true for any wave if you plug in the right velocity. Okay, we will use that equation from time to time, so get it down. Now, as I said, light comes in different wavelengths, and those different wavelengths characterize the different kinds of radiation. Radio waves are very long wavelengths. Meters are certainly more than microscopic lengths. Radio waves can be anything from, what, a few centimeters to 10 centimeters or something. I don't remember exactly where the radio spectrum begins. It can go up to anything. Arbitrarily long wavelengths are called still radio waves, even though no radio could work on the basis of waves that had a wavelength of 1 billion light years. But still, they're still called radio waves. And what's the smallest radio wave? I think about 10 centimeters. All right, it's small. And it's a highly arbitrary division, of course, completely arbitrary. What's smaller than radio waves? Smaller wavelength? Microwaves. Microwaves go from a few centimeters down to what, micrometer or something like that, micron. Smaller wavelength than microwaves, infrared waves, and then from infrared waves you have light waves, visible light. Visible light is a rather narrow range of frequencies or wavelengths, and then comes ultraviolet, shorter wavelengths, X-rays, and gamma rays. Gamma rays are just exactly these objects here. Very, very short wavelength, extremely short wavelength radiation, and that's what Becquerel had discovered coming out of there. The only trouble is that Becquerel discovered discrete bumps, discrete blips, one at a time, and not nice continuous waves. Okay, that then brings us to the puzzle of quantum mechanics. Now, we're not going to go into it in any great depth, certainly not tonight, but let's just recount the history a little bit. Einstein and Planck realized, for a variety of reasons, mostly thermodynamic properties of light, that light had to be thought of as being made up out of discrete, indivisible elements. It might have been an experimental discovery. In fact, in some sense, Becquerel's discovery was an experimental discovery. It's just he didn't realize the thing he was seeing was electromagnetic radiation. So I won't go through the actual history, but let's make up an imaginary history of how the discreteness of light might have been discovered. It could have been discovered this way. You, again, shine your light on a screen, and you illuminate the screen, and of course what you see is a nice continuous blob of light. It could either be an interference pattern, or it could just be a single hole, in which case it would just be a blob on the screen. Okay. But now you do the experiment differently. Here's your source of light. You put an obstruction in the way. The obstruction is a filter. The obstruction is not a filter, but a semi-transparent, semi-opaque thing which blocks out a certain percentage of the light. What happens over here? Well, the blob gets dimmer. Okay? It's not as intense. You make it thicker. It's even less intense. You see less light arriving per unit of time. And you make it even a little bit thicker, and at some point, all of a sudden, the character of what's here changes, and instead of seeing the blob, you see discrete events, little blips. Now, if you wait a long time, these little blips build up, and they build up to something which has exactly the same pattern as the blob had. So the blob in this case, then, is some sort of effect that has to do with lots of little blips, so many little blips that you can't recognize them as being individual. That's the blob. But if you attenuate the light and cut it down so that the intensity coming through here is really, really small, what you see is blips. This experiment can actually be done. It was not done in those early days, but you can imagine. And this is what Einstein had suggested really does happen in his photoelectric paper, that light comes through as absolutely discrete things. The motivation for it was thermodynamics and other things, But this might have been the form of discovering these individual blips on the screen. And this is what really would happen. So, something very, very confusing going on. Light is a wave. That had already been proved. In fact, if we put a screen over here with two little holes in it, we will again see light coming through bit by bit. One at a time. And if we leave it up there a long time, the blips will sort of fill in, and what they will form is an interference pattern. So it became clear that clear but still very confusing, that light is made up out of indivisible elements called photons, and that the wave character of the light really represents, or the wave pattern really represents, the probability that the photon appears at different places. In other words, it's randomly arriving blips, but they arrive with a probability in different locations, which follows the pattern that was established by the wave theory. The wave theory gives you a wave theory of probabilities. That's quantum mechanics. We will have to talk about quantum mechanics a great deal more. But this kind of experiment, this kind of observation about light was the first example of a connection, which is really, in a sense, what this course is all about. It's a connection, first of all, between waves of any kind and particles. They are not two different things. Somehow, waves and particles are two manifestations of the same thing. We'll have to come back to that, and we'll try to explain it perhaps again later. Now I'm just filling in some early facts, mostly just to set the stage. Waves and particles, at least when it came to light, were somehow intimately connected, and it didn't make sense to say light is a particle, or it didn't make sense to say light is a wave, but has manifestations of both. All right, the situation only got more complicated when electrons were studied. Electrons are clearly particles. Everybody knows electrons are particles. There was no ambiguity about that, no more ambiguity than there was about whether light was a wave or not. It was. But yet, something funny. Well, something funny also happened with electrons. You could do exactly the same kind of experiment with electrons. You can. Today, this experiment can really be done. At the time, it was a bit of a thought experiment, but equivalent experiments, you'd have to put the holes, you have to make a screen. You put the holes much closer to each other if you want to do it with electrons for one reason or another. And you send electrons through. Of course they come through one at a time. Everybody knew electrons were little particles that came through one at a time. What was totally unexpected is, or would have been unexpected, was that the electrons, when you open two holes, form an interference pattern. So it wasn't just that light was funny. Particles were funny in general. Electrons exhibited wave properties. Light exhibited particle properties. In fact, had we taken the alpha particles, which are much heavier than electrons, much, much heavier than electrons, 8,000 times heavier than an electron, much harder to do these kind of experiments with, but send them through two little holes like that, we also would see interference patterns. This has been done with objects which are much, much bigger than helium nuclei, namely buckyballs. Buckyballs have been sent through interference experiments like this and seen to form the same kind of interference pattern. So, everybody know what a buckyball is? 60 carbons, 60
In the shape of a soccer ball.
In the shape of a generalized soccer ball, yeah, right. Is it a regular? Is a regular soccer ball got 6? Yeah, like a soccer ball. No, it's not. It's not really a soccer ball, but well. So, and it is widely believed that if you did it with bowling balls, well, you can't really do it with bowling balls. Much, much, much too hard. I understand the people who did it with buckyballs are going to try to do it with living cells, viruses, to prove that viruses are quantum mechanical. And then they're going to ask the virus what the virus felt when it... Anyway, good. The waves and particles are somehow the same thing. And if you want to penetrate that more deeply, you've got to learn some quantum mechanics, and the place to do it is in my lectures, which don't cost anything. They're on the internet. Okay, that's, now let's talk about the properties of photons a little bit. Photons are these discrete, indivisible elements of light. Light has energy. If you absorb the sunlight, it heats things, obviously has energy. So therefore, photons have energy. What do we know about the energy of a photon? Photons being indivisible, we know the energy must come in very discrete packets. Now, what is a photon characterized by? Or a light wave. Imagine a light wave coming in, composed out of these discrete photons. Don't try to picture it. It's impossible to picture. When the light wave actually falls on a screen, it forms these little dots, so it's particles. Made of particles, but we see some sort of wave phenomena associated with it. The wave phenomena is associated with a wavelength and therefore a frequency, an angular frequency. We discover that that light wave is made up out of discrete units, each with an indivisible bit of energy, cannot be subdivided, and the energy of one photon, the energy of every single photon in this light beam with a given wavelength and a given frequency is given by a number called h bar, Planck's constant, one of Planck's constants. H bar times omega. In other words, omega is large when the wavelength is short. The shorter the wavelength, the larger the frequency. The larger the frequency or the shorter the wavelength, the larger the energy in every photon. So, first lesson. Short wavelength photons have lots of energy. Long wavelength individual photons have very low energy. Now, of course, a radio wave can carry a huge amount of energy. There's no question you can make radio waves with lots and lots of energy. How do you make radio waves with lots of energy? You pile lots of photons up. Many, many photons, all with the same wavelength and the same frequency, but there is something, nevertheless, some remnant of the discreteness. Namely, the energy of such a wave is always an integer multiple. This is the energy of a photon. The energy of a light ray, let's just call it a ray, or a light wave, is some integer number, some integer multiple of h bar omega. All right, so the light rays come in indivisible units. Every light ray, every pulse of light with a given frequency and wavelength has an integer multiple of energy in units of h bar omega. All right, so this is an important equation here. This equation is of absolute central importance to understanding why particle physics is the way it is. In particular, it's very, very central to the question of why we have to build big, giant machines to see smaller and smaller objects. My grandson's not a kid, he's 26 years old, but he asked me one day, how come you have to build bigger and bigger machines to see smaller and smaller things. Why don't you build small machines to see? All right, we're going to try to answer that question, but this is the central fact, that the energy is proportional to the frequency of a single photon. All right, we've been through waves and particles, photons carrying discrete units of energy. I want to come to another set of concepts now. We're certainly not abandoning this line of thought here, but there's another line of thought that I want to remind you of, mostly remind you of. Not quantum mechanics, but the special theory of relativity. Special theory of relativity plays a very important role in particle physics. Particle physics is, in a sense, relativistic quantum mechanics, the combination of relativity and quantum mechanics. And so let me just remind you of one particular simple fact and then be clear about what that fact means. Most famous equation of physics, E equals mc squared. This equation also plays a very important role in the reason that in explaining why particle physics is the way it is. Energy is mc squared. Let's just be very clear about what it means. In the early days of relativity, people spoke of the rest mass of an object and the moving mass of an object. The moving mass and the rest mass were different. The mass of an object was minimum when it was standing still, but when it moved, the mass increases. You still read that in elementary physics textbooks, but you never read it in any work of modern physics. You never read that the mass of an object depends on its state of motion. It's largely a change in language. The change in language is such that what we now call mass is what used to be called rest mass, period. Whenever I refer to a mass of an object, I am talking about its rest mass. All electrons have exactly the same rest mass. All electrons have exactly the same mass, period. If you look up the masses of particles in a table of masses and so forth, you will not find them called rest mass. You will just find them called mass. So from now on, we will never speak about the rest mass. We will speak about the mass of the electron as a number that experimental physicists measure in great detail. Every electron has exactly the same mass as every other electron. And the mass is not something which depends on the state of motion. But of course, the energy is something which depends on the state of motion. The faster an electron moves, the more kinetic energy it has. So there's something wrong with this equation. Yes, there's something wrong with this equation. This equation is no longer, even though it's the most famous equation in physics, it's not the right equation, at least with modern terminology. Energy is only equal to mass times c squared for an object at rest. Okay? The right way to say it is the energy of an object at rest if the object has no net motion. Now, it could be a complicated object with all sorts of internal motions, but it could be a box of gas, all the molecules flying around like mad. But as long as the box of gas is itself stationary, then we speak of its rest mass, and we can speak of its rest energy, the energy of that box of gas when it's standing still. And Einstein's equation says that the rest energy of an object is the rest mass, or just the mass, times the speed of light squared. Now what exactly, let me imagine two experiments that you might do to confirm this, just to understand precisely what it means. You take a pot of, not a pot, a box with molecules in it, and you put it on a scale to measure its weight or its mass. And draw a scale. The molecules are cold. You begin with the box of gas very, very cold, and you measure the mass. Sorry, you measure the mass. You get some number. Now you feed some energy into the box. You heat it up. You heat up the molecules in here. You increase their energy. The box is still at rest. The molecules are not. The molecules are moving around, but the box is at rest. And we can ask, what is the rest mass of the box of gas? The answer is, if you increase the energy by adding thermal energy, you add a certain number of calories or a certain number of joules, joule is a unit of energy, to the box, you will discover that the box's mass, the box of gas, its mass increases, its weight increases. Okay? Now, the amount that it would increase is so tiny. If you increase the temperature by 1,000 degrees or something, it's so tiny that it would be quite unmeasurable. But in principle, this is the meaning of E equals mc squared. An object at rest, if you add energy to it, its mass increases, its weight increases. Also, its inertia increases. Harder to move it. Okay. Another example. Now, this example is not something that you can really do, but the other example is something that is, real experimental physics, observational physics. You start with an electron and a positron. We haven't talked about antiparticles. Let's just ignore the fact that we haven't talked about them for a moment. Two kinds of particles, electrons which have negative charge, positrons which have positive charge. They have exactly the same mass, precisely the same mass. They are in every respect similar, except for the fact that they have opposite electric charge. Because they have opposite electric charge, they can combine and disappear. They have plus charge and a minus charge. The net charge is 0. Nothing prevents them from disappearing. Well, something does prevent them from disappearing. They have energy. Each one has an energy. Let's suppose these two particles are at rest. We bring them together. Each one has an energy equal to mc squared. So the total energy is twice mc squared. Well, mc squared for each particle. We bring them together, that energy can't disappear. Energy is conserved. What happens to that energy? That energy becomes photons. Photons go out. You bring an electron next to a positron, and you let them annihilate, poof, out go photons. The photons, in some sense, are energy. They can be absorbed by a material and heat the material. They can be converted to all forms of energy. And how much energy do you get by annihilating an electron and a positron? The answer is twice the mass of an electron times the speed of light squared. It's a tiny amount of energy. I mean, if you just had one electron and positron, you couldn't do much with it. You need, huge numbers of them to heat a cup of coffee, but still, in principle, that's what happens. And of course, this is an observational fact. That's the meaning of E equals mc squared. And another way to really say it, which I think is the right way to say it, is to say energy and mass, at least for an object at rest, are the same thing. Why do we have to have an equation? Really, it's just a conversion of units from what we call mass units to what we call energy units. And this tells you the conversion, roughly like a conversion from meters to centimeters or whatever. This is the conversion between energy units and mass units. All right? But in any case, if you know the mass of an object and you want to know how much energy you would get if it disappeared, you multiply by the square of the speed of light. So you get a lot of energy for a small amount of mass. What is the speed of light and what is Planck's constant? Let's write down the numerical values of the speed of light and Planck's constant. We need them, one for here and one for here. Photon energy.
On the E equals mc squared? Does the mass have to have a mechanism for the energy to be released, or?
Well, does it have to? Yes, it has to have a mechanism, and we haven't talked about that mechanism, but just let's stand on the outside and say, look, this thing happens. An electron and a positron, when you put them together, will just disappear. Let's not ask what the mechanism is. The one thing we know is, independent of the mechanism, energy should be conserved. If E equals mc squared for the electrons, that energy has to show up somewhere. So there are some things you say without knowing what the mechanism is. Conservation laws, where you know that certain things are conserved, you can often say important things about a system without knowing detailed mechanisms. Okay, let's talk about numbers. The speed of light is a very big number. Planck's constant is a very small number. How do I know it's a small number? Well, the energy of a photon is a tiny amount of energy. The frequency of a light wave is very large, so it better be that h bar is a small number. Let's write them down. Okay, so c, the speed of light, that is equal to 2.99762,458. I'm not kidding you, this is true. Plus or minus something in the last digit over here, times 10 to the 8th meters per second. Units. Units are important. You know, it's not just 2.99762,458 times 10 to the 8th. It's that number of meters per second. That's the speed of light. How about Planck's constant? Everybody, of course, will memorize this number because it's important to this class that you know that number. 1 point, same thing here, memorize this one. 1.0545571628 times 10 to the minus 34. Very small number. And what are the units? Anybody know what the units are? I worked out the units, but I think I erased them. Energy times time, right. Well, what are the units of energy? Mass times velocity squared, right? mc squared. Better be mc squared. Mass times velocity. It's mass, kilograms, times length squared over time squared. That's energy. And Planck's constant has another unit of length in it. Another unit of time. Okay. So Planck's constant is measured in, what's the unit of mass? Kilograms. Kilograms, meters squared, divided by seconds. So why are these numbers so crazy? Why are they so big? Why are they so small? Why are they so odd? I mean, is nature playing some awful joke on us to put these, to make these numbers so awkward? Or are people just being foolish in using peculiar units? For example, the speed of light is something which depends on your choice of units. If you measure it, instead of measuring it in meters per second, you measure it in feet per hours, you will get a different answer. So there's nothing sacred about this number. It depends on the choice of units, length units in this case, and time units. You could certainly work with units in which the speed of light was a more convenient number. You could work with units in which the speed of light was 1. The units would be light years per year, for example. The speed of light is 1 light year per year, or 1 light second per second. So it's not hard to choose the speed of light to be 1. You just use different units of space and time. Same is true of Planck's constant. You can use units in which Planck's constant is equal to 1. But why is it that we actually use such peculiar units? How come the people who invented units, Mr. Metric or whoever he was, the British are worse than the metric system, of course. They were really perverse. 5,280 feet in a mile. How many pounds in a stone? 16. I don't know where they got these units from. I don't know. Is a stone 16 pounds? I can't. 14 pounds. Even worse. 16 is at least divisible by 2 4 times, but okay. 14 pounds.
How high is your horse?
Hmm?
How many hands high is your horse?
That's another good one. How about horsepower? Yeah, I mean, just bizarre units. Metric units are better, but they're also very, very arbitrary. For example, the meter had to do with how far a man's hand is from his nose. Why? Because it was measuring length of rope or something. So these are highly arbitrary units and have more to do with biology than they have to do with physics. They have to do with biology in the sense that the real question is not why a meter is what it is, why a meter is what it is. It's a question of why an arm has to have X number of molecules in it. And there's nothing special about these numbers. All right. Given that, you can ask, are there units? Are there better choices of units of the 3 units? What do we need? We need 3 units. We need a length. The 3 things that the 3 kinds of units we need are length, meters or feet or whatever, time, seconds or years or hours or something else, and mass. All of the other units in physics can be re-expressed in terms of these. This is a complete set of units. There are 3 of them, and we can choose them in various ways. For example, instead of using the kilogram, we could use the mass of a proton as the basic unit of mass, or the mass of the sun, or and so forth. Use different units of mass. Certain things in astrophysics are a lot easier, not easier, but a lot smaller. The equations are simpler. They involve less constants, fewer constants, if you use units in which the mass of the sun is 1. Okay? Equations in nuclear physics are simpler, only simpler in the sense that they don't involve as many arbitrary constants if you use units in which the mass of a proton is 1. So you can make your equation simpler and get rid of these weird numbers. And how many numbers can you get rid of? How many numbers can you get rid of these? Well, you have a choice of 3 units, mass, length, and time, and that means you can simplify 3 of the constants of nature, or 3 of these type of constants here, and set them equal to 1 if you like. So in astrophysics or in cosmology, you might want to use the light year. That's a much better unit than the centimeter. And if you use the light year and also the year, light year for distance, year for time, speed of light comes out 1, of course. So we can simplify 3 numbers. Usually, and what do we do? All right, so the question of which numbers we simplify might depend on what kind of physics we're doing. If we're doing astrophysics, we might want to simplify certain numbers. If we're doing atomic physics, we might want to simplify other numbers. And in particle physics, there are basically these 2 constants which we can set equal to 1 by appropriate choices of units. Appropriate choices of units can set C equal to 1. That's easy. You just use units in which time is measured in such a way that time and distance are measured in such a way that the distance something moves in 1 unit of time is 1 unit of distance. You can also set h bar equal to 1. And you have your choice about 1 other unit. What's a good unit to set equal to 1? What's a good unit, a mass unit, to set equal to 1 in particle physics? Well, you could use, what about the proton? Why not the proton? Or why not the Higgs boson? Or why not the mu particle? Or, well, the answer is obvious that there isn't the best. There is no particularly good unit of mass which will simplify particle physics so that at best you can set one arbitrary particle to have a mass of 1. And that would be foolish because there would be no particular reason to focus on any one particle. What about why do we pick the speed of light and Planck's constant?
They appear in so many equations.
Well, they do appear in so many equations, but so does the mass of the proton, or the size of the proton. Why? Okay, I'll tell you why. There are two very, very fundamental facts about Planck's constant and the speed of light, and the way that I'll say it is just to say the words. No object in nature moves faster than the speed of light. It doesn't matter what it is, no matter how you try to accelerate it, you can get it up closer and closer to the speed of light, but you can't pass the speed of light. Right? For any object in nature, any. Right? So there's something universal about the speed of light. It's a universal bound, universal for all forms of matter, for anything that we can make. It has a certain universality. All objects are constrained by the speed of light. So it has some reason to be thought of as something universal. What about Planck's constant? Does Planck's constant come into anything where you would want to say everything in the world necessarily has precisely this property? It's the uncertainty principle. We haven't discussed the uncertainty principle, but all objects in nature, the precision with which you can measure their positions and velocities and momenta are constrained by exactly the same constant. The uncertainty in position times the uncertainty in momenta are always constrained to be as big or bigger than Planck's constant. Again, everything, all particles, not just particles, but objects of all kind are constrained by the same number. Right? So it's for that reason, the specialness of these two constants, that it makes a lot of sense to set them equal to 1. The size of the proton, for example, or not the size of the well, let's say the size of the proton or the mass of the proton, there's nothing very special about the proton. The proton is one of hundreds of one of hundreds of objects. Why didn't we set the mass of, give me some weird element from up there, rubidium. Why didn't we set the mass of a rubidium atom to 1? Because you say rubidium is not in any way more special than plutonium. Okay? You're learning about my chemistry knowledge. Okay? There's nothing special about rubidium. It's just one of many. Same thing is true of the proton. It's just one of many. The electron is one of many. So there's nothing universal about it. Is there a third universal quantity which is so special that we might want to set it equal to 1? Something which everything is constrained by. Yeah, the trouble is electric charge is a dimensionless quantity. But yes, we could, the electric charge is a fundamental constant like that. Gravity. Right. What can we say? We can say all objects in nature attract each other with a force which is equal to the product of the mass divided by the square of the distance between them times Newton's constant. We don't make any exceptions. It's not that there are some objects which do that and other objects which don't. Incidentally, in the case of the electric charge, of course, there are neutral particles, so not all objects interact in the same way electrically, but everything in the world interacts exactly the same way, product of the masses divided by the square of the distance between them times Newton's constant. So Newton's constant is one of these very universal things. G. I don't know, what is it, 6.749833154. I assure you it's not known to anything like that kind of precision. I think it's 6.7 times 10 to the minus 11th in some units or other. It's another thing that it makes a lot of sense to set equal to 1. Why don't we do it in particle physics? The reason is that particle physics is totally insensitive to gravity. The gravitational force between objects in particle physics is absolutely negligible. So gravity would be a stupid thing to set equal to 1 because gravity just doesn't come into the equations of particle physics. Particles are too light to experience significant amounts of gravity. Particles that we know about today are just too light to experience any significant gravity. And so there's no particular value, since none of the equations in particle physics involve g. It's better to leave it alone, just go away, and not fix one of the units. Just leave it free.
Isn't it even fair to say that making the assumption that you're dismissing it, in fact,
What's that?
isn't it fair to say that particle physics dismisses it all the time because it would be insignificant? You actually don't even, it's not even fair to assume that G is dismissible, that in fact the particles you're examining at these high energies may not be subject to gravity in the classical way we know.
Well, of course, we know that they are subject to gravity. If you take enough particles, they form the Earth. And you take another enough particle.
Not when they're split apart.
Yeah. So that's right. We don't really know what how elementary particles. Well, no, we do. Well, we can certainly take one elementary particle and see how it behaves in the field of the Earth, see whether it falls, and they do. Single particles do fall in the field of the Earth. But how single particles would influence each other gravitationally, that of course has never been measured. And so, yeah, it's possible to question whether the universal law of gravitation applies to particles. I don't think many physicists do question it, but the main point is a practical point. There's no benefit gotten by setting G equal to 1 in particle physics because G just doesn't come into particle physics, at least in current versions of particle physics.
There are other attractions, such as attraction to 2 electrons or the other forces. Wouldn't it make sense
Are you talking about gravitational attraction?
physics to set those to 1
Which?
instead of G?
Which?
The attraction of 2 electrons, for example.
Electrons don't attract, they repel, but yeah.
But,
Yeah, you could do that.
but that doesn't go into your particle physics either.
It does go into your particle physics. Right, it does. It does. Yes, you could use units, and we often do, in which the electric charge is equal to 1.
And the attraction, the repulsion,
Yeah.
is the third constant. which
Yeah,
you
it's-
could force.
You
to
could. Traditionally, we haven't. Yeah, traditionally we haven't. There's a reason that we haven't, and we'll eventually get to it.
Wasn't that your point about the electric charge being dimensionless? Once you set C at H bar to be dimensionless, the charge is also dimensionless?
Yeah, the charge is equal to 1 over 100. The square of the charge is equal to 1 over 137 is a dimensionless measure of the charge. And it's a completely dimensionless number. And we'll come to it. We'll come to what it means. You could.
Coulomb's constant is 1, you're saying? Or would that be the third one if you did Coulomb's
Well, you
constant?
can't set 1 over 137 equal to 1. So there's an obstruction to.
Because Coulomb's constant, you can set it for 1. Actually, when I took physics, that's what they did. That was the third one. They set Coulomb's constant.
Who's constant?
Coulomb's? Coulomb's.
Coulomb. Yeah. Yeah, you could. Right. You could. For whatever reason, historically, we haven't done that. And there's probably no particular benefit in it. In any case, we will use units in which C and H bar are equal to 1. Quite often, not always, but sometimes. Only when I want to illustrate the size of numbers will I put C and H bar back into equations. So we Oh, some equations come out very simpler, yeah. If we set C equal to 1, then E is equal to M. That's it. Energy and mass are just the same thing. We had another equation over here. E of energy for a photon. This is the energy of a massive particle which has some rest mass. Energy of a photon is equal to h bar omega. Well, the equation simplifies. If we set h bar equal to 1, energy is just equal to frequency. So that's just an illustration of the use of, what's that? No. Well, yes, but not for a photon. Photons have no mass. Don't forget, this is, okay, there's a difference between these two, the meaning of E in these equations. In this equation, it's rest mass and rest energy. But photons can never be brought to rest. Nevertheless, they do have energy, but it's not rest energy. It's basically kinetic energy. Photons have kinetic energy, energy of motion, so this is just plain energy, whatever the energy is, and it's equal to their frequency. So they're two different, yeah.
Well, mass and rest energy are relativistic because what is zero? What is rest? It has to be relative to something.
Yeah. Yeah, no. Just forget the word rest now.
No,
Just forget the word rest.
You just use it to differentiate them, but what is mass at rest in the universe? Where would it be?
Not in the universe, it's in the laboratory we're talking about.
Yeah, and then it becomes relative to the...
Relative to the laboratory, energies are measured relative to the laboratory. Energies are different depending on the state of motion of the observer. If you have a photon or anything else and two different observers observing it, they see two different energies. Obviously, even in Newtonian physics that's true. If I have an object here and I see it, I say it has no kinetic energy. Right? You're running by at 100 miles an hour, you look at it and you see that it has kinetic energy. So energy is something, both sides, yeah. Energy is something that depends on the state of motion of an object. It makes sense to ask what the energy of this cup of coffee is when it's at rest. Then it's just the internal motion of the molecules and so forth, and no overall kinetic energy. That's the thing which is the M, when you write energy is equal to mass.
Right, but all I'm saying is that the counter that it's sitting on is not at rest.
What's that?
In the universe, the counter it's sitting on is not at rest.
Okay.
I mean, if it's at rest, then it's at rest relative to something else.
Yes, and the point is that energy is measured relative to a given frame of reference. Energy is not a universal thing that everybody will agree on. Right? It's relative to a particular frame of reference. So relative to my frame of reference, the energy of this cup of coffee, when it's standing still relative to me, is equal to its mass. Okay.
Question. Earlier this evening, again, on this whole subject of naming things and constant, you didn't like frequency, cycles per second. You said physicists use omega, 2 pi.
To some extent, that's a historical fact.
My question is, it seems to me, 2 pi, using radian 57, whatever, 2 pi times that, is more complicated than a complete cycle.
I agree with you.
Why would one use something that appears to be more complex than a single cycle?
Good question. Good question.
Engineering math gets simpler if you do that. Engineering math.
Yeah. I mean, there's some mathematical simplicity to radians that is. I think the answer is you look at all the equations you write down, you write them in both terms of frequencies and you write them in terms of omegas. And you see in which form do you encounter fewer factors of 2 pi. I'm not sure what the answer to that is.
It's omega. Omega, for sure. It's simpler.
You think so?
Oh, yeah.
Okay.
Yeah, if you do a lot of things with e to the I something, or
Yeah.
logarithms or anything.
That's right.
Question, practically speaking, is it possible to accelerate two particles fast enough with enough energy that they will interact gravitationally?
In principle, certainly.
I mean, but practically speaking, like large hadron colliders, that's pretty small.
Very far from it. Very, very far from it. No. Of course, it depends on what you mean by a particle. I don't think you'd want to call the Earth a particle. But, no, well, what's elementary? You know, yeah.
What is the source of positron?
What's it?
A source of positron.
What is the source of positrons? High energy collisions.
That's the only way to do it?
You need it. Yeah, you need a collision to create positrons.
Nuclear process.
Yeah, nuclear processes. Yeah. So
We used,
nuclear decay sometimes yield positrons.
we used Planck's constant, Planck time and Planck distance and things like that.
Well, we're not doing that. Planck time and Planck distance correspond to setting G equal to 1. Yeah, so we're not doing that. Now, one of the reasons that we might not want to do that is once you set 3 of these equal to 1, let's say, then you have a natural unit of length, a natural unit of time, and a natural unit of mass. The natural unit of length, when you set G equal to 1 and all of them equal to 1, is called the Planck length. And it's very, very much smaller than anything that comes up in normal particle physics. So you would not want to measure particle sizes, particle radii, and so forth in units of the Planck length. It's just too small. It's much smaller than anything that occurs in. So that's the reason for not doing it.
You'd use it like in black holes or cosmology or...
Yeah. Anything that really involves gravity and quantum mechanics together and relativity, it makes sense to put all 3 of them to 1. But if only 2 of them are important, you may only want to set 2 of the constants equal to 1. Okay, let's see. I want to go a little bit further. Yeah, let's go a little bit further with the basic concepts that we'll draw on over and over. I mean, today I'm just listing basically the preliminary concepts, practically establishing language, energy, mass, particles, waves, fields. Let's talk about another concept that comes up over and over in particle physics. In fact, it comes up over and over in almost all physics. Momentum. Momentum, if you take an object and it's at rest, it has no momentum at all. It may have energy, it has E equals mc squared energy, but it has no momentum, an object at rest. If it's moving, it typically has momentum. Momentum is conserved, just like energy. When 2 objects hit each other, the net amount of momentum doesn't change. So momentum is a conserved quantity. And because it's a conserved quantity, it has an importance. Anything that's conserved is important. Momentum is a combination of the mass of an object, or better yet, its energy, and its direction of motion. Its mass, its velocity, and its direction of motion. It's a vector quantity. It's a vector quantity, and as a rule, it's proportional, or as a vector quantity, it points along the direction of motion of an object. It points along its velocity. For a non-relativistic object, an object moving with much slower than the speed of light, the momentum, of course, is equal to the mass times the velocity. The arrow on top means that it's a vector quantity. It has a direction. Okay, so mass times velocity is momentum in non-relativistic physics, but it's not quite the right expression for in relativistic physics. And in particular, it's not quite the right thing for things moving with the speed of light. So let's talk about light. Does light have, first of all, does light have energy? Yes. A beam of light shining on something heats it. Does light have momentum? Now, ordinary light, if it hits you in the chest or something, doesn't give you much of a push. Why? It's because the light is so dilute and it just doesn't have much of a kick. Okay? But if you got hit by this laser beam that they make in, where is it, in across the bay on the other side, what's that place? Livermore, yeah. They got this great big laser, and that laser shines its light, and when it hits a piece of material, it just implodes it. What is it that's imploding it? It's the momentum of the light, just pure, sheer momentum. And it can be huge. So yes, light has momentum, and a pulse of light moving along, let's imagine a pulse of light moving along the x-axis. Every pulse of light moving along a given direction. Now, of course, real light might have some dispersion. It might, some of it might go out. Some parts of the light wave may go one way. Some parts may go the other way. But if the light is very collimated, so that it's moving along a particular axis, then the right formula, now I'm not going to prove this. I'm not going to prove it. I'm just going to tell you the right formula for a light beam is that it is the energy of the light beam divided by the speed of light. Let me just compare it with this. Or another way to write it is the energy is C times P, but let's leave it in this form here. Now, let me just compare these two things. Momentum is mass times velocity. Momentum is energy divided by velocity. Just a simple question. Are they dimensionally the same? Are they dimensionally the same? So to inquire whether they're dimensionally the same, all you have to remember is that the dimensions of energy are mass times the speed of light squared. So just in terms of units, energy is like mc squared divided by c just tells you that the momentum of a beam of light is its mass times its velocity. Not really its mass. Its mass, the mass of a light beam is really zero. It has no mass, rest mass. But in terms of units, it's equal to an energy times c squared, sorry, a mass times c squared divided by c. You get the point? It's just a question of units. This doesn't look like this in terms of units. One has a velocity upstairs, one has a velocity downstairs, but it is the same in units when you remember that E equals mc squared. Okay, so this is the formula for the momentum or the relationship between the momentum and the energy of a light beam. And it points in the direction along the motion. That's right. That's right. How to write this? Let's just say the magnitude of it points along the direction of the light beam, but the magnitude of the momentum is equal to the energy divided by c. The magnitude of the momentum. The direction is along the direction of axis of the light beam, along the direction of motion of the light beam, but the magnitude of the momentum, the size of it, is equal to the energy of the light beam divided by the speed of light, c. Okay? You can see now momentum is energy divided by c. That's why the momentum is so small. You can detect the energy of a light beam. Sure you can. It heats up a little bit of water. It evaporates water and so forth. It's not hard to detect the energy, but it's quite hard to detect the momentum of the light beam, and that's because there's this c in the denominator here. Momentum of a light beam is very small, typically. Of course, as I said, if you pump up the light beam enough, it can give quite a kick. All right, so that, let's do one little exercise. All right, let's just, The momentum of a light beam is its energy divided by the speed of light. Now, we had a formula. Do you remember the formula for the energy of a photon? Let's take one photon now. One photon is an example of a light beam. Let's figure out what the momentum of a photon is. So it is equal to its energy divided by the speed of light, but what's the energy of a photon? H bar omega. So the momentum in magnitude is equal to h bar omega divided by the speed of light. Now, do you remember the relationship between frequency, wavelength, and the speed of light? We had that before, that, yeah, what was it? The frequency times wavelength is equal to c, right? Frequency times wavelength, and now if I put omega here, omega times lambda is what? 2 pi times c or 2 pi divided by c? 2 pi times c, right? 2 pi times c. No? 2 pi? C over 2 pi? C over 2 pi. Good. C over 2 pi. Is that right?
It's easier if you just stay with 3.
Wait, omega is bigger than f. Omega is bigger than f, right? All right. Yeah, right. So wait a minute. I don't believe you. I don't believe you. I got to do it myself. We have frequency times lambda equals c, right? So therefore, yeah. So now, wait. Omega is equal to 2 pi times frequency. Right. So frequency is omega over 2 pi. So this is omega over 2 pi. And I say that omega times lambda is 2 pi times c. I was right. All right. Omega times lambda is 2 pi c. So let's get rid of the omega here and write omega is equal to 2 pi c over lambda. I've just divided by lambda. Let's just see what we get. We get momentum of a photon is h bar divided by c, and now times omega, and omega is 2 pi over lambda times c. The c's cancel out. That's good, because I know the c's should cancel out. And what do we find? We find the momentum of a photon is 2 pi h bar, that's a number, divided by the wavelength. What? What's that? Yeah. 2 pi h bar equals h, right. Right, that's right. Right, so P is also equal to just old-fashioned h divided by lambda. There's an example where where it was possibly not so smart to use h bar. Right, okay. Look, the 2 pi's are going to get you one way or another. Someplace they're going to get you. The pi's always come up somewhere. You can't get rid of them. Okay, what does this say? This says the shorter the wavelength, the larger the momentum of a photon. A single photon of a radio wave has a very, very small momentum. A single photon of a gamma ray is a very, very short wavelength photon, has a good kick to it. One photon, it won't hit, it's still a pretty small kick. But what this is telling you is that the momentum is related to the wavelength. The shorter the wavelength, the bigger the momentum. That is an extremely important lesson, that the shorter the wavelength, the bigger the momentum, and also, of course, the bigger the energy. The energy and the momentum are related or proportional to each other. So if you try to make very short wavelength photons, the result will be that you have to spend a lot of energy to make them. Now it becomes clear why physicists have to build bigger and bigger machines to see smaller and smaller things. And the reason is, if you want to see a small thing, you have to use short wavelengths. If you tried to take a picture of me with radio waves, I would look like a blur. If you wanted to see any sort of distinctness to my features, you would have to use wavelengths which are shorter than the size of my head. If you wanted to see a little hair on my head, you would have to use wavelengths which are as small as the thickness of the hair on my head. The smaller the object that you want to see in a microscope, the shorter the wavelength of light that you have to use. Okay? If you want to see an atom, literally see what's going on in an atom, you'll have to illuminate it with radiation whose wavelength is as short as the size of the atom. But that means the shorter the wavelength, the smaller the object you want to see, the larger the momentum of the photons that you would have to use to see it. So if you want to see really small things, you have to use make very high energy particles, very high energy photons or very high energy particles of different types. How do you make high energy particles? You accelerate them in bigger and bigger accelerators. You have to pump more and more energy into them to make very high energy particles. So this equation and its near relative, what is its near relative? E equals h bar omega. These two equations are sort of the central theme of particle physics, that particle physics progresses by making higher and higher energy particles, because the higher and higher energy particles have shorter and shorter wavelengths and allow you to see smaller and smaller structures. That's the pattern that has held sway over basically a century of particle physics, or almost a century of particle physics. The striving for smaller and smaller distances, that's obviously what you want to do. You want to see smaller and smaller things. And at the same time, the striving for shorter and shorter wavelengths, which means either higher and higher momentum or higher and higher energy particles.
Is there a theoretical limit? Is there a limit to shorter and shorter wavelengths?
Yeah, we think there is. Well, yes and no. Yes, in some sense, yes. We think when you get down to the Planck length, something new begins to happen. And we can talk about that at some point in these lectures, where it may bottom out. But we're very far from the place where it bottoms out. If it bottoms out, it probably bottoms out at the Planck length, which is, 17 orders of magnitude smaller scale than what we're trying to see at the LHC. So we've got a long ways to go, a very long ways to go, even if it does bottom out. All right, those are the basic facts that I wanted to get out in front of you. They sort of determine largely how particle physics has progressed, and as I said, it has progressed by going at every stage to shorter and shorter wavelengths, larger and larger momentum and energy, and smaller objects.
Question. Would there be any heuristic saying that the wavelength or the size of the particle you want to look at is inversely related to the size of the cyclotron you're building? I realize it's a ridiculous ratio, but is that sort of, you need 1 mile per...
Roughly speaking, yes, that's correct. Roughly speaking, that's right. If you have a given capacity to accelerate, now what determines your capacity to accelerate? The size of the electric and the magnetic fields that you can create. So let's suppose you take the largest fields that you can create in a magnet made of steel this big, and that determines your ability to accelerate. Ability to accelerate means the energy that you can pump into something per meter. Given a meter of accelerator, how much energy can you pump in? All right, so to double the amount of energy that slack produces, it would have to be twice as long. Or round, but that's right. But round gives you another problem. The problem that round gives you is that when particles move in circular orbits, they radiate. And when they radiate, they lose energy. So let's take the case of a linear accelerator. The longer the linear accelerator is, the higher the energy that you can pump the particles to. and pretty much linearly proportional to the size of the accelerator.
And it's going to get double the resolution?
Yeah.
So basically, resolution times size is a constant. Order of
Rough, yeah. Yeah. So if you wanted to get to this Planck length, how big an accelerator would you have to have? Well, as I said, 17 orders of magnitude longer than the CERN accelerator.
Known universe?
No, I think it's more like the galaxy.
The ring engineer.
Yeah, I call it the Gedankatron. Right. Right. Yeah.
How high are the energies of cosmic ray compared to what you get in the IHC?
Higher. I mean, the highest cosmic ray energies are 10 to the 21 electron volts or something like that, which is 21 minus 9 is what? Quick, 21 minus 9, 12. 10 to the 12th GeV, whereas the accelerator in, well, no, it actually doesn't work. The highest energy cosmic rays are 10 to the 12th GeV. But the problem is, you see, the problem is cosmic rays, they may have this huge energy, but they hit stationary targets. Whereas in the accelerated CERN, they're going to be colliding targets. And so you get more bang for your buck from the colliding particles. But still, cosmic rays have much more energy than, effective energy than the accelerators. The problem with them is in order to really do good experiments, you have to have a huge flux of particles. You can't do an experiment with one high energy particle. It will probably miss your target, or it probably won't be a good dead-on, head-on collision. You don't learn anything from that. You learn very little from that. So what you want is enough flux of particles so that you have a good chance of having a significant number of head-on collisions. That takes a lot of particles when the targets are small. So I told you how big an accelerator you would have to make. Now I would tell you how many particles have to collide in order to see something interesting. And I once worked out how much energy it would take to fuel this accelerator in order that you could do experiments in a reasonable amount of time. And I think I got something like 100 trillion barrels of oil a second. So you need the accelerator as big as the galaxy being fueled by something. I think it was 100 trillion barrels of oil a second, and it's going to be a while till we do experiments like that. Yeah. Yeah. Right. But these are real distance scales. I mean, they really do come into physics, and the puzzle and the question is how to probe them, how to get at them without being able to spend 100 billion barrels of oil and build a galactic-size accelerator.
So
Not
what's
easy.
the GeV energy level hoped for from the LHC?
Is it hopeful in what sense? In what sense would you ask is it hopeful?
Compared to this 10 to the 12 GeV you get from, that you need from...
It's not comparable to the 10 to the 12 GeV from, no. When you have a particle hitting a stationary target, take that 10 to the 12 and take its square root. It's 10 to the 6th. It's like having 10 to the 6th GeV in colliding particles, each one colliding. So if you have two particles colliding, each one with 10 to the 6th GeV, it's like having one particle with 10 to the 12th hitting a stationary particle. Now 10 to the 6th, that's 1,000,000 GeV, that's 1,000 TeV. So we're still very low compared to what cosmic rays can do. But if you have a handful of cosmic rays coming in, the chances are that it's going to do an interesting collision are negligible.
For more, please visit us at stanford.edu.